In this video, we're going to explain the heat transfer problems that were introduced during large group on October 7th. Kind of show you a little bit of the demonstration that we did in the auditorium, and then go through the calculations involved in that problem and one additional problem after that. At the end of the video, there'll be one problem left on your assignment, and that is your one to complete before we see you in small group during this next week. So if you work on that and get stuck, bring your questions to class. Otherwise, do your best to complete it and see if you can't get the correct answer, which I'll share with you at the end of the video. So in this video, in large group, we introduced the idea of heat lost equals heat gained. And the idea there is that in any situation where an object is getting cooler and giving off heat in joules, or if an object is getting warmer and gaining or absorbing heat in joules, those joules have to be going or coming from somewhere. In other words, if I'm cooling and releasing heat, where's it going? Well, it has to be going somewhere else and being absorbed by something else. If I'm getting warmer, where is that heat coming from? It has to be released by something else. And in our example in the large group, the idea was that we took a warmer material and mixed it with a cooler material and measured how the heat transfer could be measured in our temperature measurements, in our temperature probes that we used to kind of follow the temperature as it changed over the course of a minute or two when those two things were mixed. So here's the basic idea. Heat lost by an object cooling off, the heat lost by that object is equal to the amount of heat gained by its surroundings or by the object to which it's giving that heat. And the idea that we share with you in large group was basically that if I had a cup of warm water, there isn't actually any water in here, but we're going to explain kind of how we did it in large group. If I have a cup of warm water containing an amount of water at a certain temperature, and I take that warmer water and I pour it into a container containing a cooler liquid, the identity of which is unknown at the beginning of our demonstration, then the temperature of our cooler liquid will get warmer as the heat from our warmer water is transferred into it. So as I combine the two of these, pour the water into the cooler liquid, for example, the temperature of my combined liquids will be somewhere in between the warmer original water temperature and the cooler original unknown liquid temperature. And I'll share with you the data that we gathered during the large group, and you can see kind of how we worked out the calculations on that. So in the large group, what we did, Mr. Mitchell filled these two cups or two containers with a certain amount of water and a certain amount of unknown liquid. He just kind of poured a random amount into those, and then we measured the mass of each and the starting temperature or initial temperature of each. So data for the water side of it, and I'll put this up on your screen here for you, or on the worksheet that you've hopefully got. And if not, you can copy this information down into any notebook place. But the temperature and the mass data for the water first of all. So what we had to start out the problem here, and I'll turn on my tablet here and give you some data. Let's zip it down to the chart. Here we have on the two sides of our chart here the information for our water, which was the warmer of the two, and then the information for our unknown liquid. So for the water, our example in the large group, Mr. Mitchell measured out and used 73.74 grams of water. And just kind of poured a random amount in there. And it was warm water. He had it in a thermos. And we stuck a thermometer in there. Okay, so he had a couple of these vernier temperature probes hooked up to a LabQuest on his laptop and was showing the data up on the screen. And I'll kind of show you what that graph looks like approximately. When we combine the warm and cool liquids together. But he used a couple thermometer probes like these, and we measured the initial temperature of the water when it was fairly warm at 58.54 degrees Celsius. So that was our warmer water to start out with, or our warmer material. And then the unknown liquid, we poured some of that in there too in the cup. I've got it here just kind of marked for your reference. It was the cooler material, so he poured a certain amount or a random amount of that liquid into that cup, and that was a cooler sort of room temperature liquid. And the information that we gathered for that on our unknown liquid, which was our cooler one, actually why don't you let me clean that out and put it in blue so we can kind of visualize the blue here. For our cooler liquid, the mass of it was 90.64 grams, and the starting temperature of it was 21.19 degrees Celsius. So 21.19 degrees Celsius. We're right around room temperature. So once we had the mass and the initial temperatures recorded for both the water and the unknown liquid, we poured them together. And so the warmer water got cooler and the cooler liquid got warmer, and they met somewhere in the middle. Now, if you look at this graph, this is a sort of a reproduction of what we did in the large group. The graph didn't look quite like this, but it looks approximately like this. And you can see here that the warmer water started out, again, at a temperature of around, we said 58.54 degrees. So that's kind of up here in the corner. And the cooler liquid started at a temperature at around room temperature, around 21.19 degrees Celsius. And then as they mixed, the temperature of the cool liquid came up, and the temperature of the warm water came down, and they met somewhere kind of in the middle over here. So that key temperature then is the TF. This is our temperature final temperature for the two of them combined, and we measured that temperature to be 44.85 degrees Celsius. So you can see that the water got cooler by about, we'll calculate here, about 14 degrees, and the unknown liquid got warmer by about 23 odd degrees. And so what we'll do here is go back up to the chart, back up to the table, and we'll use that 44.85, our temperature final, for both of them. This temperature final is relevant for both the water, which cooled down to that temperature, and for the other liquid, which warmed up to that temperature. That same number they have in common. That's really important in these heat change problems because they met in the middle, if you will. And then what we also know in our data table here is that water has a specific heat of 4.184 joules per gram Celsius, which is a number that if you've been keeping up with the homework or doing the problems in class, you've probably heard a lot. But basically, we know everything about water. We know its mass, we know its starting and ending temperature, we know its specific heat. On the unknown liquid side, we know the mass and we know the starting and ending temperatures, but we don't know its specific heat. So in this problem in the large group, our basic goal was for you guys to calculate the unknown specific heat. And that's actually right there at the top of the page in the description of what we're doing. We can solve for the unknown specific heat of a liquid. So that's what we're about to do. To do that, what you want to do is start your math with the side where you do know everything. Okay? Now, we don't know everything for the unknown liquid, but we do know everything for the water. So that's where we'll start. And what I'm just going to do here is, if I can, move all my stuff here out of the way, just kind of get it out of our hair so we can do our math here. Now that we've used the graph to get our data, we don't need it necessarily as much. But let's start with the water side, and we'll do our math. So for the water, let me zoom that back in so you guys can see it a bit better. For the water, we know all the information that we need to calculate heat. We know mass, we know temperature change, and we know specific heat. So we'll work out the calculations on our water side first. And for that, we'll need the specific heat equation, which we've been using in class. Q equals M times C, the specific heat, times delta T, change in temperature. So what we know here is that the mass is, again in our data table here, 73.74 grams of water, which is just the amount that Mr. Mitchell poured in. We know the specific heat of water, 4.184 joules per gram Celsius. And we know delta T, or we can find it. So to find delta T, we'll take these two temperatures, right, and we'll bring them down and we'll subtract to find delta T. Delta T is always TF minus TI, final temp minus initial temp. And so for us, that would be our ending temp, 44.85, minus our starting temp, 58.54. And again, if we do our subtraction there, we get our delta T. Now, I'll save you the trouble. If you want to go punch that into your calculator, you can. But that number is going to come down right here and drop in as delta T. And that's negative 13.69 degrees Celsius. So it went down about 14 degrees. Now it's negative to show that the water was getting cooler, and that negative will be important then in our Q. So if we punch that into our calculators and let it do all the math for us, we'll end up with Q, our heat, and our answer here is negative 4,224 joules. Now that means, again, that that's the amount of heat lost. This is the heat that was lost by the water and transferred to the unknown liquid, which gained the same amount. Now it's important to remember that the negative sign here, if you remember on our answer for Q, this negative means the heat was lost. Whenever you see a negative sign, that's just to kind of imply more like a vector in math, where it's telling you the heat is being released or given off by the material that's cooling in temperature here. You can't actually have a negative amount of heat, measure a negative amount of heat. We're simply measuring a loss of a positive amount of heat. And so that negative is really just there to remind us that it's a heat loss. Why does that matter? Why am I harping on that so much? Well, the idea is that that amount of heat is 4,224 joules, and that's the amount of heat that was gained on the other side. In fact, we're going to take that amount and call it the amount of heat that was gained by the unknown liquid. Okay, that's our same Q. 4,224 joules. All that heat was given from one to the other, and we're going to use it here as a positive because, again, it's a gained. We're not going to show it as negative 4,224. We're going to show it as positive 4,224 joules. And our job in our math here is to calculate the specific heat of our unknown liquid. So again, we need mc delta T. The same equation is true for our unknown liquid, except we have a different set of data here because, of course, all the values are different. So if I go back to my chart, I know my mass is 90.64 grams. Hopefully you've been filling that in on your own chart. The specific heat is what we're looking for. We don't know what that is. That's kind of our X here. And then delta T is going to be different here. Remember, delta T is different for each material because they started and ended at different temperatures. So we're going to use 21.19 and 44.85 to find our delta T. Our final temperature was 44.85. Our starting temperature was 21.19. And so our delta T, it drops in right here, is a positive this time of 23.66 degrees. So the temperature went up by 23 or almost 24 degrees. So in this case, to rearrange and solve for our specific heat, which is what we're looking to find, we'd need to divide both sides by both the mass and the delta T. And I'll go ahead and show that here. You don't necessarily need to work out and show that each time. If you can rearrange it mathematically and sort of show it in your answer, that you're able to rearrange it in the algebra here. I don't think necessarily writing this out on every problem is necessary, but we'll do it on this one so that we've got it as an example. So I'll divide both sides. Oops, let's clean that up. Divide both sides by my mass and my delta T, and that'll leave specific heat standing alone as the mass cancels and the delta T cancels. So if I punch all this on the left side into my calculator, I'll have my specific heat and let the calculator do all the magic, and in the end my answer comes out to be 1.96. Now remember what that means, or what the units are on that, are hiding right here in the problem. Joules per gram degree Celsius, 1.96. Just a quick comparison, that specific heat for our unknown liquid is less than half the specific heat of water, which we'd used earlier as 4.184. And what that means is that water would get warmer using twice the energy, or you could think about it as water would get warmer half as fast as unknown liquid X does here, because it takes more than twice as much energy to warm a gram of water as compared to raising the temperature of a gram of my unknown liquid by 1 degree. 4.184 versus 1.96. Now, what we did talk about in class was that we would take this then as our answer and kind of see if it matches any liquids that we could look up in a chart. So what liquids out there, what everyday common liquids, have a specific heat of around 1.96? And you could look at a list of those, or we could give you a list to kind of consider, or we could ask you to go research that and see what liquids that might be. Turns out that in large group we talked about the fact, and it actually revealed at the end, that our unknown liquid here was ethanol, basically 95% ethanol, which we have around for chemistry in our stockroom. We compared this a little bit to the actual specific heat of our ethanol, which was actually quite a bit higher, and we could theoretically then go ahead and calculate percent error and do some comparisons and things like that. But we won't bother with that here. We didn't bother with it in large group either. The idea being that we can estimate the specific heat experimentally for an unknown liquid simply by measuring this heat transfer between one known thing and an unknown thing. In this case, water was our known, and liquid, an unknown liquid, or we call it liquid X, was our unknown material. In a lab, we might take the same sort of data and actually see if we can calculate and estimate the specific heat for maybe a solid material like a metal or something. And the same kind of idea could hold. So that's our math. There's our problem. If you're watching this on your computer and you want to do a screen capture or something, you could certainly do that. Hopefully you've been working out along with yourself, with us on your own paper there, so that you've got all the calculations and the math to show too. So keep in mind, on one side of our math is going to be heat lost, and then we'll compare that or transfer that literally, just like in the reality of our lab, transfer that value over to the other side and use it as our heat gained. So heat lost is equal to heat gained. We could also, in a given problem, calculate the heat gained and flip it over to the other side and use it as the heat lost. I think in question number 3, on the back side of this same page, you'll be asked to do something where that's exactly what the problem will have you do. So let's look at the example problems, or these extra example problems, on the back of the page. So what we did in large group was spend a few minutes at the end of the hour going through the math on the extra example problem here, and actually sort of calculating, showing how you'd get to the answer on this one as well. So I'll take you through this one so that you have the same examples to work from that the people who were in large group were able to get. And if you were present for large group and you're watching this more as kind of a follow-up or for a review, then this should be pretty familiar to you. And we'll work it out the same way we did there. So this question says we've got a 1,023 gram piece of iron at 343 degrees Celsius, and we're putting it into water. So with about a kilogram, pretty good chunk of iron here. How much water is needed at 25 degrees Celsius if one wants the final temperature of the system to be 32.3 degrees Celsius? And it tells you, keep in mind, the specific heat of iron is 0.450 joules per gram Celsius. Now, there's one little typo on here, and we did have the class fix it while we were in large group. So here it says how much water is needed at 25 degrees Celsius. This should be if. Okay. If one, like you or me, if one wants the final temperature of the system to be at 32.3 degrees Celsius. That's a typo. It doesn't really change the math, but it does clarify the meaning of the sentence just a little bit. So let's go through this and do the math together. What we have here again is iron. We have the iron and we have the water. It's kind of our two sides. One is transferring heat to the other. And just like we did with our two liquids in the previous example, we're going to need M. Oops, let's put it in the middle like we did in large group. We're going to need mass. We're going to need specific heat. And we're going to need our initial temperature, which we abbreviate as TI. And we're going to need our final temperature, which we abbreviate as TF. Okay, pardon my penmanship. So to fill this in, the mass of the iron is given 1,023 grams of iron. Okay? The water's mass is what we're after here. We don't know how much. It wants to know how much water is needed. Okay? So that's our answer that we're looking to find. We had a 1,023 gram piece of iron, so we've used that as our mass. The specific heat of iron we know because it's given in the problem. And if it wasn't, you could go Google it, search it somewhere, or look it up on a periodic table or something like that. They're kind of published all over the place. Try that again, 0.450. And for water, we do need to use waters, again, 4.184, that familiar number. On the other side, with our temperatures, our iron sample starts at 343 degrees Celsius. And its final temperature, the whole system's final temperature, is 32.3 degrees. So it's cooling down a whole lot. On the other hand, the water starts out at a temperature of 25 degrees Celsius. So the water's cool. I'm going to call it 25.0. And the final temperature, again, on that is the same. Remember, the hot object and the warm object come together here and meet in the middle, or between the two at least. In this case, a whole lot closer to the water than the iron's temperature. And the final temperature for both is 32.3 degrees Celsius. Now, one thing in our little data table here as far as calculating Q, that mass times specific heat times delta T. So truthfully, in our data table here, we won't need initial and final temperature alone, but we'll also need that delta T. So let's go ahead and calculate that for both sides. To find the final temperature, to find the change in temperature for the iron, rather, we need to take final minus initial. So the metal is starting at 343 degrees and ending at 32.3 degrees. So to find delta T here, we're going to take 32.3, the final, minus 343, the initial, and that's a major drop-off in temperature. It went down by 310.7 degrees Celsius. Now we're kind of throwing out the rules of rounding, but that's okay for our problems here. So there's our delta T. It's getting cooler by over 300 degrees Celsius. On the other side, the water is starting out at 25 and going up to 32.3. So perhaps you can do that one just in your head fairly easily, but we'll work it out here just for the purposes of having it in front of us. It's ending at 32.3 and starting at 25. So a change in temperature of 7.3 degrees. Okay, a delta T. So one's getting cooler by 310 degrees, one's getting warmer by about 7 degrees. They don't meet in the middle. You don't simply average their two temperatures on any problem to find that final temperature. Either that's given or you might be asked to calculate that. Okay, so now we need to move on to our calculations. And so in this problem, what we need to decide here is as the iron is cooling off dramatically, how much heat is it losing? We know everything for the iron. We don't know everything for the water. So we'll start with the iron side. And this, again, because the iron's getting cooler, we'll have to do with our heat lost. Heat lost is Q times is set equal to the mass of 1,023 grams times the specific heat of iron, which is in the problem, it's 0.450, times the change in temperature, which was negative 310.7 degrees, so a drop in temp. How much heat then was lost by the iron as it cooled? Well, punch that into my calculator, and I'm going to get a pretty good sized answer here, considering it dropped 300 degrees. My Q comes out to be negative 143,031 joules. Now, again, we're not really following the rules of rounding, but we'll assume for right now that that's not a terribly important thing to show today. This is the amount of heat lost. Again, the heat lost is 143,031 joules. The negative sign simply shows us that it's being lost. So the heat lost is 143,031 joules. And remember that the negative is simply there as part of the word lost, or the verb to be lost. So the amount of heat is a positive quantity, always. And the negative is just there to show which way it's being transferred, either taken in as a plus or given off as a minus. So we're going to take that heat lost and also use it as the heat gained. So the heat gained by our water, will be that same amount, 143,031 joules. And since that's our Q, we're going to go ahead and calculate, just like before, an unknown on the other side of the equation. The mass of our water, that's what we're looking for. How much water did it take to accomplish this temperature change? The specific heat of water, 4.184 joules per gram Celsius. And our delta T, the water warmed by 7.3 degrees. Final calculation, I'm going to keep that a little bit lower actually. Our final calculation then is to get the M by itself. So just like before, we divide both sides by the specific heat and by the temperature in order to get the mass, the M here by itself. And I'll go ahead and let you do that. The mass here works out to be 4,683 grams, okay, of water. That's how much would be needed. 4,683 grams of water would be needed. Now, just in case you have any confusion about the sign on our Q, that negative sign being there or not being there, if you were to calculate this problem, bringing that negative sign along with you, you might in the end find that your M comes out to be negative. Because if you think about it here, in this problem, if you brought that negative sign along with you and went ahead and calculated mass, you'd have had negative for our Q value, negative 143,000 instead of positive. You'd have had a positive specific heat, which is always the case. You'd have had a positive delta T because the water was getting warmer. And when you went to divide, you'd have been taking a negative divided by two positives. Now, math tells me that that's got to be a negative answer. And your answer would have said negative 4,683 grams of water. That should not make sense to us. There is no such thing as negative mass in terms of measuring a quantity of something in the lab. Either you have something with mass or you don't have something and the mass is zero. You can't have a negative mass. So in this problem, if you'd accidentally brought the negative sign along, the good news is the worst that would have happened is hopefully you'd have been puzzled at the end thinking, how the heck can I have a negative mass? It doesn't make any sense. And you'd be right, it can't. So hopefully at that point you would have been alerted to the fact that you made a mistake with your sign and you knew how to fix it. Okay. Now, that's the idea for this problem. Very similar to our first problem where we knew almost all the information for our unknown liquid and were asked to find specific heat. We rearranged and did that after we determined how much heat was lost by the water. We brought it across and used that as the heat gained by the liquid. Same thing happened in number 2. We figured out how much heat was lost by the iron and we used that as the heat gained by the water. As a preview, we're not going to solve this next question. We're going to ask you to do this one for the next time we see you in class. But as a preview, we've got water going into an aluminum pan. And the pan starts out at 26 degrees The final system temperature is 39 degrees. So the pan's actually getting warmer from when it starts to the final temp. And it's asking us to find the initial temperature of the water. So in the end, you're being asked to figure out how warm was that water when I poured it into the pan. And the pan got warmer, and we assume the water got cooler. So your job here is to calculate the initial temperature of the water. You'll still need to find Q for the side on which you know everything in order to find Q, and then take that Q across to the other side. Keep that sign switch in mind and do the best you can with it. And the answer that you should come up with here on the third question on your sheet is around 42.7 degrees Celsius. So that's your target answer. See if you can't do the math to figure that out. Get that answer, and if you get stuck on something, bring your work and your questions to class the next time you see us, and we'll help you figure out the answer to your questions then. Thanks for listening, and if you have further questions, again, see us in class or in Sabre time.